Hi Year 11, this is our fourth video for the topic of differentiation for the International Baccalaureate course Analysis and Approaches. In this video we're going to look at the derivatives of trig and inverse trig functions. Let's begin with the derivatives of trig functions. Now they are given for you on your formula sheet, which you can see below, but basically the derivative of sine x is cos x, the derivative of cos x is negative sine x, and the derivative of tan x is 1 over cos squared x, or sec squared x. Now we're going to look at the proofs of all three of these derivatives, and we'll start with the proof of the derivative of y is equal to sine x. Now it is quite a complicated proof, and you would never be expected to reproduce it in an exam. From first principles, f dash of x is equal to the limit as h approaches 0 of f of x plus h, take away f of x all over h. Now our function here is sine x, so let's substitute that in. Now it's tempting to expand this out, but it will get us absolutely nowhere. Instead, we're going to use one of the products and sums formulas. In particular, that sine of a plus b take away sine of a minus b is equal to 2 cos a sine b. Now looking at our numerator, we have sine of x plus h minus sine of x. And that kind of matches here. So we're going to let a plus b equal x plus h and a minus b equal x. And solving simultaneously, we end up with a is equal to x plus h on 2 and b is equal to h on 2. And so we can rewrite this as 2 cos x plus h on 2 sine h on 2. And so our formula for the derivative becomes the limit as h approaches 0, I've brought this 1 on h out the front, multiplied by 2 cos of x plus h on 2 sine of h on 2. Now where on earth do we go from there? Because currently, if I substitute in 0, I end up with 0 divided by 0, which is undefined. Now there's this really famous limit, which we're actually going to look at in the next video. It says that the limit as x approaches 0 of sine x on x is equal to 1. So I can see a sine h on 2 here. It'd be really nice if I had sine h on 2 divided by h on 2. Have a look what we have here. So we have 2 on h, and that's actually equal to 1 divided by h on 2. So we can rewrite this as the limit as h approaches 0 of cos of x plus h on 2 multiplied by sine of h on 2 divided by h on 2. And this here is going to equal 1 as h approaches 0. And when I substitute 0 in here, I'm going to get cos x. So the derivative of sine x is cos x. Now you'll be pleased to know that the proof of the derivative of cos x is much, much easier. So we're going to rewrite cos x as sine of pi on 2 take away x. Remember they are complementary ratios. Now we already know and have proved what the derivative of sine x is, so we're going to use that fact. Here we have a chain rule. Outside function is sine x, inside function is a power rule. So the derivative of sine of pi on 2 take away x is cos of pi on 2 take away x multiplied by the derivative of that inside function, which is negative 1. So it becomes negative cos of pi on 2 take away x, and this of course is sine x. So the derivative of cos x is negative sine x. Here's some examples. Find the derivative of y is equal to 3x cos x. So we have a product rule. U is equal to 3x, v is equal to cos x, u dashed is 3, v dashed is negative sine x. Let's construct the product rule. We have u times v dashed plus v times u dashed. And just tidying that up, the derivative is negative 3x sine x plus 3 cos x. And example 2 is a quotient rule. So we have u is equal to e to the 2x, v is equal to 3 sine x. Now the derivative here, this is a chain rule, but it's just e to the 2x multiplied by 2, and v dashed is equal to 3 cos x. Let's construct the quotient rule. We have v times u dashed, take away u, times v dashed, all over v squared. Now factorising, and then cancelling, we end up with e to the 2x multiplied by 2 sin x take cos x, all over 3 sin squared x. Let's move on to the derivative of tan x. Recall that tan x is equal to sin x divided by cos x. So to differentiate this, we're going to use the quotient rule. U is equal to sin x, v is equal to cos x, and u dashed is cos x, v dashed is negative sin x. Constructing the quotient rule, we have v multiplied by u dashed minus u multiplied by v dashed all over v squared. So let's tidy that up. We've got cos squared x plus sin squared x all over cos x all squared. And cos squared x plus sin squared x is equal to 1. So the derivative of tan x is equal to 1 over cos squared x, or sec squared x. Okay, let's turn our attention to the reciprocal functions, sec x, cosec x, and cot x. You can see the derivatives of those down the bottom. That's from your formula booklet. But let's work out the derivative of sec x. It's equal to 1 over cos x, which in index form is cos x to the power of negative 1. Now, small point, that's not the same as this. This is inverse cos or arc cos. Right, back to here, this is a chain rule. We bring the negative 1 down, cos x to the power of negative 2 times by the derivative of the inside function, which is negative sin x. And tidying that up, I end up with sin x over cos squared x, which I can write as sec x tan x. Similarly, the derivative of cosec x, well, cosec x is sin x to the power of negative 1. And again, using the chain rule, we end up with negative sin x all to the power of negative 2 multiplied by cos x, which is negative cos x divided by sin squared x, or negative cosec x cot x. And the derivative of cot x, which we're going to do slightly differently because cot x is equal to cos x divided by sin x. And so we have a quotient rule. Now I could write out u is equal to cos x and v is equal to sin x, and I encourage you to do that. But if we substitute it straight into the formula, we get this. Let's have a look. So this is v multiplied by u dashed, take away u multiplied by v dashed, all over v squared. Tidying up the numerator, we end up with negative sin squared x, take away cos squared x, and that's negative 1. Think about factorising that negative out. So we end up with negative 1 divided by sin squared x, which of course is negative cosec squared x. Okay, inverse trig functions. This is the last thing that we have to learn for this lesson. Recall, if f of x is equal to sin x, then the inverse function is inverse sine of x or arc sine x. And remember, we have to restrict the domain of f of x, otherwise the inverse function is not going to be a function. Here is y is equal to sine x, and we've restricted the domain between negative pi on 2 and positive pi on 2. And this is the inverse function, so this is arc sine x. Similarly, if f of x is equal to cos x, then the inverse function would be inverse cos or arc cos x. And just like with sine, we restrict the domain, although this time it's going to be restricted between 0 and pi. So this is y is equal to cos x, and this is arc cos x. And finally, tan x. The inverse function is inverse tan or arc tan. Here we have got y is equal to tan x, and we're restricting the domain between negative pi on 2 and positive pi on 2, although it doesn't equal either of those points because they are asymptotes. And here we have arc tan x. Okay, let's work out the derivative of arc sine x. So we're going to start by turning this around and making x the subject. X is equal to sine y. Now let's work out dx dy. That's equal to cos y. We don't want dx dy, we want dy dx, so let's invert both sides. Dy dx is equal to 1 over cos y, and we've kind of come to the end of the road, because normally we would substitute back in, and we can't. But we're going to do a sneaky trick. You've seen this before. If sine y is equal to x over 1, then we can write that. And just using Pythagoras' theorem, this side here would be the square root of 1 minus x squared, and so cos y would be equal to adjacent over hypotenuse, and so our derivative is 1 divided by the square root of 1 minus x squared. Now on your formula sheet, you get the derivatives for arc sine x, arc cos x, and arc tan x. I'll leave the derivative of arc cos x and arc tan x for you to have a go. Let's finish off with some examples. Find the derivative with respect to x of arc tan of x squared plus 1. So we have a chain rule here. We have a function inside another function. Outside function is arc tan. Inside function is a power rule. So let's start with the outside function. It's going to become 1 over 1 plus x squared plus 1 all squared. And then we're going to multiply by the derivative of the inside function, which is 2x. And just tidying that up, expanding the denominator, we end up with 2x over x to the power of 4 plus 2x squared plus 2. And example 2, find the equation of the tangent to the curve y equals arc cos x at x is equal to a half. So we'll start by finding the gradient of the tangent. So let's differentiate. The derivative of arc cos x is negative 1 all over the square root of 1 minus x squared. Now we want the gradient of the tangent at the point x is equal to a half, so let's substitute that in. At x equals a half, dy dx is equal to negative 1 divided by the square root of 1 minus a quarter. Tidying that up, we end up with negative 2 over root 3. We also need to know the point where the tangent goes through, so let's substitute a half into the function itself. At x equals a half, y is equal to arc cos of a half, which of course is equal to pi on 3. Let's substitute into the point gradient formula. M is equal to negative 2 over root 3. x1 is a half and y1 is pi on 3. And let's just expand this right-hand side and make y the subject. So y is equal to negative 2x on root 3 plus 1 on root 3 plus pi on 3. Okay, that's it for this lesson. Our next lesson we're going to return to fundamentals of calculus and look at further limits.